Hello and welcome everybody to join PyData Global 2021. My name is Zach Lee. I'm very happy to be here and be your host of this session. Please, if you feel comfortable in doing so, rename yourself to a name you would like to be called in this session. It would be lovely if you could also add your pronouns in there. If by any chance I pronounce your name incorrectly, please correct me at any time. Please note we are recording this session. Okay, I would now to welcome Barry to our session. He will talk about the risk at scale, running a large investment risk system, and how risk analysis technique can help you. And Barry leading a number of teams within a Man Alpha technology team and Man Group. Man Group is a large hedge fund investing in very wide range of asset and investment style. And now we are passing the time to Barry. Thank you.
Thanks, Zach. Let me just share my presentation. Hi, everyone. So I'm Barry Fitzgerald. As Zach said, I lead a few teams at Man Alpha technology team. We're the part of Man Group who looks after trading decision making. So the kind of technology that helps systems or people make their trading decisions. I'm going to talk a little bit today about what finance people mean when they talk about risk. I'm going to talk a bit about specific ways of quantifying market risk. And I'm also going to talk about some of the technologies in implementing those techniques. But let's just start with what is risk. So there's lots of types of risk. There's the risk a meteorite might hit a data center. There's a risk you might get injured in an automobile accident, etc. The type of risk I'm talking about today is market risk. So essentially the risk you might lose money due to market events, prices going up or down, etc. And the way I'm going to start looking at this is with this graph. I have 3 investments here. So the top one is an investment in Bitcoin over the last 2 years. The middle one is an investment in Apple, and the bottom one, which looks like, and actually is essentially just putting your money in the bank over the 2 years. And it's a question I'd often ask at interview stage for someone working in risk technology is, which of these investments is riskier than the others? And then how would you quantify that? And people can intuitively nearly always answer the first, like they can tell me Bitcoin is probably more risky than Apple, which is in turn probably more risky than just putting your money in the bank, but often struggle to quantify it. So I'm going to use some examples from a domain we're more familiar with to try to explain that. So what exactly is market risk? Well, one good way to think about it is how much money might my investment lose tomorrow. You might have made or lost lots of money in the past with your investment, or you might be brand new to an investment. But on each day, you should be comfortable. You know, if you can answer this question, you can then decide if you're comfortable with that potential loss. And if you're not comfortable with it, maybe you reduce the size of your investment, or you take hedging trades or something like that. But that's why it's useful. If you get an idea of the answer to this question, you can make decisions that affect that future. So let's move now just to a slightly different domain, but I think will help explain how we measure risk in finance. So I have 2 databases here. I've just simulated this, but request times and an individual request. And it's a very kind of easy answer for us as people working in technology. Which database would you prefer to use? The one on the left has a nice tight spread of request times, whereas the one on the right has requests spiking up to over 20 seconds. We could make this even easier to answer by transforming it to histograms. So if we take all of the request times and plot them as a histogram. Again, now this makes it like really super obvious. We can see the one on the left has a nice tight distribution of request times, whereas the one on the right has this long tail. We can see like an individual request took 25 seconds. And it makes it very easy to choose between the 2 of these. But a downside of looking at it like this is this works extremely well if we're comparing 2 databases. But if we had let's say 20 databases and 20 query types on each, just the space constraints and interpretation, if we were going to show hundreds of these types of charts, it becomes lost in the noise. So there's always a desire, both in kind of performance management and monitoring, and in financial risk, to narrow this down to can we get a kind of a summary number that we can display a lot of numbers on a single page. We can have a table of numbers for 20 databases very easily. And so to do that, then we start looking at percentiles, and this is a very common technique in monitoring. We can say 50% of requests take longer than 10 seconds. 1% of requests take longer than 20 seconds. Just from those two numbers, you can imagine if I had 20 databases, I could very quickly start identifying which databases were slow, which were faster. At times, I may need to delve into the detail of looking at the distribution if I really wanted to diagnose things. But as a summary stat, this is super useful. We want to do something similar for financial risk, and we can do a very similar approach to this for finance. So, for example, using my chart at the top, if we took the returns of Bitcoin and we took daily percentage returns and formed a histogram of those, we could then choose a point on that distribution and say we have a 1% chance of losing more than Y% or Y dollars tomorrow. So by using this, by assuming tomorrow's returns will follow a similar distribution to the historic returns, we can get a good estimate of what we might lose tomorrow. And that's a very, if we did that in turn for Bitcoin, Apple, and our investment in just putting our money in the bank, we would see very different numbers. It would be a very easy way to quantify the risk of those investments. But this is widely used across the industry. It's actually in some regulations you have to use this, or have to at least have looked at this. And it has lots of advantages. It's computationally very efficient. It's quite easy to calculate. It's very interpretable. If you tell someone you have a 1% chance of losing 10% tomorrow, you can actually show them, well, on these days in the past, if something similar happened, you would lose this much of your portfolio. So there's no fancy maths. It's all very interpretable. But there's lots of problems with it too, and I'll discuss some of those. So I think this is fine. Dog illustrates one of the problems here, that the past history of something happening doesn't necessarily mean it's not going to happen tomorrow. A really good example of this is companies. We know companies go bust and go out of existence all the time. But for a company we've invested in, by definition, it still exists. So even though we know there is some chance of it going bust tomorrow, that won't be represented by our historical value at risk model. And that's a problem that we want to fix. Also, you only have a limited number of data points. There have only been so many points in daily returns in the past. Bitcoin has only existed for so many years. And then also the returns for 5 years ago in Bitcoin might have very different properties to now. So there's lots of issues with this approach. So it's still very useful, but there's some issues that can be improved upon. So one way of doing this is quite standard. Like, you would fit your historic returns to a normal distribution, then calculating the mean and standard deviation, you can start calculating, analytically, what the percentile chance of things are. I think, at the moment, I think we have 126 people in this video conference. If I took everyone's height and fitted it to a normal distribution, I could come up with a pretty good estimate of what are the chances of a 7-foot person being the next person joining this conference. And that's even if we have no one who is 7 foot in the talk at the moment. So it allows us to make predictions of things that haven't happened yet in quite an accurate way. Again, this is widely used, very understandable. There's a little bit more maths rather than the historic value at risk, but it is quite often used as well. But in turn, there's problems with this approach. So let's think about some of those. So market return distributions are not normal. There have been cases in the recent past of seeing 180 standard deviation moves in a market. That shouldn't happen in the lifetime of the universe if a distribution was normal. And it happens maybe not 180 standard deviations, but large standard deviation moves happen a lot more often than a normal distribution would suggest. Different assets have very different return distributions. So investing like an insurance or a bond will have very different to an equity return distribution. And then also we tend not to invest in single instruments. We invest across lots of different securities and lots of different stocks, and your pension would be invested in many individual stocks. They aren't independent. When the price of oil moves, the price of airlines also moves, possibly in an opposite direction. Those correlations change over time. The distributions themselves change over time. So combining all of those to come up with like a single distribution that describes your total portfolio's returns is it's extremely hard and not really mathematically or practical to do so. So it's not to say we do use normal distributions, and normal distributions are used for certain cases, but when you're looking at extreme tail events, they tend to be quite poor at that. And then there are just computational issues with combining lots of distributions too. So what do we do next? So there's Monte Carlo analysis. So I'll do a brief aside to talk about what Monte Carlo analysis is and how it can help in this scenario. So personal story, I was once trapped on a desert island, and a genie came along and told me that he'd free me from the desert island if I could give him the first 10 digits of pi. And I hadn't memorized one of these nice mnemonics for the first 10 digits. Obviously, this isn't a true story, but imagine if we had to do this with no tools, no calculator, no laptop, what would you do? So one way of solving this with Monte Carlo analysis is to draw in the sand a square, and within that a circle. And then you could start throwing stones at that square and counting up how many have landed inside the circle and getting the ratio of that to the ones that land within the square. If you miss the square altogether, you can just ignore that stone. This will give quite, depending on how many stones you throw, this will give quite an accurate estimate of pi. And I think, as you know, this is a data conference, we can all tell this is the type of algorithm that computers are extremely good at. We can sample millions or billions of simulated stone throws and calculate it. And then also we can estimate how accurate up to this point our estimate of pi is. So we can decide, do we throw more stones, do we throw less stones, depending on the use case. The real power of this is this works with an extremely limited knowledge of pi. There's no fancy maths here. It's like, you know, the derivation of that is very trivial. But still it can lead to quite an accurate estimate of pi. And this can be used across a number of different domains. If you have a vague view of what the distribution of results are, you can use Monte Carlo analysis without describing it mathematically to get a good estimate. So it is used in lots of other domains. So I think Fogbugs, for example, uses it to do project estimation or task estimation. If you have some data set on how long tasks have taken in the past, you could form a distribution from that and then use Monte Carlo sampling to see, you know, how much could you expect, you know, an outlier project to take in the future. Even for the example I gave of database requests, if there is some absolute hard limit you can never breach, you could use Monte Carlo analysis to say, well, how likely is that? You may never have had a single database query of a particular type take longer than an hour, for example. But using Monte Carlo analysis, you could potentially start to look at what's the probability of tomorrow one actually taking an hour. So it's a very useful technique because it makes no assumptions really about the underlying maths of what you're trying to estimate. So how does this apply to finance? So what we do is we take historic returns and the correlations of those returns and some random seeding, transform those into like random distributions for each asset, There's definitely complexity there that the random distributions have to be related according to the correlations. So there is some quite fancy maths in getting that to work. But then from that, we can form essentially a big list of hypothetical days, like on the first row there. On this hypothetical day, we believe asset 1 will go up 1%, 2 down 5%, and asset 3 up 2%. And we know from our correlations and the historic returns that's a believable day. It is something we think could happen. If we do that hundreds, thousands, tens of thousands, millions of times, we can start forming a distribution for our overall portfolio and pick out a point on the distribution and estimate the value at risk. So we would say like the VAR 99, so the 99th percentile loss would be 1%, 2%, 10%, depending on the portfolio. So this is widely used, somewhat a gold standard for complex portfolios, especially as you get into mixed asset classes and so on. Widely used across the industry. There's lots of challenges calculating that, and especially it can be challenging. It requires quite a lot of infrastructure to put this in place. So I'm going to talk a little bit about that. So some of the challenges are, I'm always loath to say big data. No matter how much data you say these days, someone will tell you it's not big data. Such and such is big data. But in this case, there are quite large quantities of data. We also need to do many, many simulations to get kind of an accurate view of the risk. So like going back to my example, it's like you need a lot of stone throws before you start getting, you start smoothing out the random effects. There's lots of, like any big data or data science task, a lot of the work is in cleansing the data, looking at the conventions of the data, how's it been scaled, has it had FX applied or not applied, all that kind of stuff, like in common to kind of any of these data tasks. Some of the steps are extremely CPU intensive, so they need to be, there's a kind of a scaling problem there. And some of them scale quite poorly with number of assets. Like, so some of the aspects of it scale kind of in an n cubed way, which makes, I think, asset classes difficult at times. There's ways around it, but it's a challenge there. And then the last one, the non-additive results, you can't do this at a kind of an individual level and just add it up all at the end. You essentially have to, there's parts of it you can do individually, but the final answer of what my VAR is, you can't do for portions of a portfolio and add it up, because parts of the portfolio might be correlated, they might contribute to each other and so on. So it isn't a typical store it all in a data warehouse and then add it up type problem. So what about the technology we use for this? This is kind of a slightly simplified version of the kind of workflow we use. Everything's predominantly in Python. Starts off with a kind of a typical ETL job where we get positions and third-party market returns and stuff from data vendors and from other internal systems. From that, we form a graph of calculations that calculate the ingredients that we need for value at risk. So that's like the correlation matrix, and then the simulated returns and P&L vectors, so profit and loss vectors. From that, in turn, then we can calculate, we run a calculation engine on top of that. That combines those ingredients to give us the answers we want. And then we serve it up to the users. We still have quite a lot of PDFs. It's quite hard. I'll talk about this a little bit. It's quite hard to get rid of PDFs. People really like them, even though it's kind of an old technology, but I guess they're quite simple to produce for us, but have some downsides too. More and more we're moving to kind of interactive tools on people's mobiles, mostly web apps for this. And a growing thing that we're happy to serve is, more often than ever now, people are asking for Python APIs. They don't trust nice formatting, or they don't trust a nicely formatted report. They say, please just give me the data, give me an API to the data, and then they'll play with it to themselves in Python. And that definitely builds up a level of trust. And it's also definitely lower cost to produce than creating interactive tools or a fancily formatted report. So it's something we're happy to do. I'll talk about some of the other technology choices over the next few slides. But most of this is in Python, obviously with NumPy and C where needed. and pandas and so on, but it's predominantly a Python shop, obviously not the front end with React and TypeScript there. So just some of the choices we've made. We use Airflow as a workflow engine. It started off as a cron replacement for us, but now we do make use a lot of its tools for directed graphs. It has a very nice GUI, has a large range of integrations. It does have some magic. It's quite complex. I think a good sign is it's tending towards simplicity. Like the version 2 of it is actually simpler than version 1, which is a good trend to have. I think overall this is Airflow is a net plus, and I would happily recommend it to anyone. I think this space is quite immature though, that Airflow kind of set a new benchmark for these type of tools, and now some competitors are starting to emerge, like things like Pachyderm, Prefect, etc. So it'll be an interesting space, I think, to watch over the next few years to see will something new come along that is better again than Airflow. But overall, definitely worth looking at for these kind of big batch processes. Arctic, full disclaimer here, Arctic is a data store that was written and open sourced by Man Group, so this isn't a unbiased opinion here, but suffice to say, it's a very fast data store for time series and data frames, very easy to use. It's very fit to our needs for financial data and so on, but equally applicable for, I think, most kind of data frame storage use cases. It's on our GitHub, have a look at it. We've done a lot of work on it internally recently as well. So I'd recommend anyone to have a look at it on GitHub, and also watch the space for announcements. There could be a new version coming soon. And then next, Jupyter Hub. I guess everyone here probably has heard of Jupyter Hub, but I think just a slightly different spin on this that has surprised me. We made Jupyter Hub available at Man under, a web link Python. Its usage has astounded me. It's used in HR now. It's used in compliance, in legal, in sales, everywhere. I think there is a real demand from users and non-traditional users that if you provide these tools to them, they can make use of it. They can gain efficiencies for themselves with these tools. And it has only been a net positive for us. It's led to us running more Python internal training courses and running them not just for technologists and people working on kind of quantity aspects of it, but for literally everyone in the firm. And we quite strongly now say at some point in the near future, we expect every employee at Man, regardless of where they work, will probably be using Python. Now, will we get to quite that 100%? Probably not, but I think it's a very good goal to have, and we're definitely seeing huge benefits for that. So I'd urge you, if you in your organization really think outside the traditional use cases of technology and Python and data science, people will find a use for these tools. It's like Excel on steroids. I think people have described Python and pandas, which I think if you work in one of these environments where they've been using Excel for everything for many years, that's quite high praise. Next one I'll talk about is ClickHouse. So some aspects of value at risk aren't additive. We do have lots of additive stuff as well. So if you need very, very fast OLAP style querying over billions of rows, ClickHouse can really be a game changer. In our experience, it's allowed us to build web tools that look over huge quantities of data, billions of rows with hundreds and low thousands of columns, and do aggregations fast enough for interactive use, so in many cases sub-second query times. There's a huge feature set. We haven't pushed on the features, but there's definitely potential for future use there. And at the moment, where our needs have been solved by single node deployments on Kubernetes, so we haven't kind of investigated the clustering story and so on. But I would say this is a real case of, if your use case fits into this kind of niche, ClickHouse is definitely something that's worth looking at. It's been quite powerful for us. What's next for us? We're looking to start moving off some legacy technology, some stuff not shown on the diagram. It's always easier to turn on new systems than switch off old things. So there's always that aspect of the work. There's a move to GPUs. Are there aspects of this pipelines like where GPU usage would help a lot? There's a move to cloud, and how can we use cloud more? Mostly we run this internally. There's pros and cons of cloud, but it's something we want to investigate a bit more. I mentioned it a little bit, but the move away from PDFs to more interactive tools also. And then this kind of explosion of the use of Python has also started making us think more about, if we're writing APIs, we really need to think about the developer experience as well. How do you write an API that's very easy for someone who isn't a full-time technologist to use, that it works as expected, and so on. So it's kind of like developer experience rather than the kind of more traditional user experience with websites and so on.
Hi, Barry. Just want to let you know we have 5 minutes left. We want to take any question from the audience.
Yeah, so good timing. So next slide is questions. So I'm happy to
we got a question from Germany. He's asking how do you do that transformation of Fitzgerald return plus correlation to random distribution? What's the point of creating those random distribution?
It's with some quite fancy maths. I'm not sure how to explain it on a Zoom call, but I can point you some, maybe afterwards in Slack, I can point you some directions. So you start with random numbers, you transform them into normal distributions, you apply the correlation structure on top of that, and then we transform the distributions into something that's more representative of the market returns. So we essentially fatten the tails and add skew to them. There's various mathematical steps that go there. That's actually the part that's very CPU intensive and quite hard to parallelize as well. But I can definitely point you on Slack afterwards to some of some books that describe that process.
Okay, another question is in the chat room. They're asking, who is the end user of those products? Do any of those come to the client directly, or it is used as a recommendation for stock or asset to buy?
Okay, yes, I see now. So a large amount of use of this is internal use. So for the risk team themselves, who has oversight across our investments at Man Group, for the portfolio managers who are making the investment decisions, and then some of it does go to the clients directly. Is it a recommendation of stocks and assets to buy? A lot of it is after the fact of buying things, where you use this type of information to say, this is your current portfolio, this is the risk. Sometimes we do also use it in a hypothetical way. So I have this portfolio, I'm thinking about trading this, so whether that's a system deciding that or that's a person deciding that, and then we would run these risk numbers on this new hypothetical portfolio, and that may inform the decision whether or not to buy that.
Okay, so many questions in the chat box and Q&As. And one more question is, what 1% of your work is for compliant version? What percent is to work driving profit or value?
I would say, it's a good question. I would say a very high amount is towards driving profit and values. We do definitely have regulatory limits and compliance limits. We tend to try stay far away from those. So it is more of a discussion of like, where, are we taking risks in areas where we think we have an edge, or we think we can add value? And are there risks we're taking that aren't intentional? So for an example of that, it might be, we have different investment teams. If they all invested in oil, that might mean that overall we have more of a risk in oil than we intend. And so these risk systems would inform that, and then we could take action on that.
Okay, our time is over. Could you kindly move to the discussion, to the snack or get a time? And Barry, thank you so much for talk and being part of the PyData Global 2021. Thank you so much.
Thank you, everyone.